Chapter 12, Correlations. Section 12.1, Motivation and Description of Correlation. Correlation and its non-normalized sibling covariance are ubiquitous in statistics and machine learning and form the foundation for many advanced analyses, including principal components analysis, finance portfolio optimization, signal processing, climate models, and image processing. To motivate a correlation analysis, let me remind you of the goal of a t-test, and in particular, the paired samples t-test. The goal of a paired samples t-test is to determine whether the average of one experimental condition is different from the average of another condition. When computing averages, individual differences are ignored. Indeed, not only are individual differences ignored in the t-test, you actually want minimal individual differences because individual variability will increase the denominator of the t-statistic, making the effect less likely to be statistically significant. A correlation analysis, on the other hand, is entirely focused on capturing individual variability. Indeed, a correlation analysis is pointless in a dataset without individual differences. Furthermore, the average value is ignored, indeed specifically removed. Thus, a t-test compares means while ignoring individual variability, whereas a correlation ignores means while comparing individual differences. Here is an example. Imagine we want to know whether there is a familial link in preference for death metal music. So we ask 40 pairs of male-female siblings to rate their preference for death metal, and thus our data set has 40 rows, one row per pair, and 2 columns, one for brother, one for the sister. Now, we could run a t-test on these data to determine whether preference for death metal is higher in males than in females, but the research question at hand concerns a familial component in preferences. So to answer this question, we can ask whether brothers who like death metal have sisters who also like death metal. Enter the correlation analysis. We can plot brothers' preferences against sisters' preferences and use a correlation analysis to test for a relationship. A positive correlation coefficient would produce evidence for a familial component to death metal preference. Footnote. Actually, a more rigorous investigation of this hypothesis would include siblings, fraternal twins, and identical twins to isolate the contribution of genetics versus shared environment, but I think you get the idea of the correlation. This paragraph references figure 12.1, which shows a scatter plot showing that preferences for death metal is related in siblings. These are all fake data. We have a scatter plot with brothers' ratings on the x-axis and sisters' ratings on the y-axis. And there are 40 dots, 40 colored squares corresponding to each sibling pair. And we see that there is a positive relationship. The title of the plot is Death Metal Preferences in Siblings R equals 0.75. Section 12.1.1, the correlation coefficient. The goal of a correlation analysis is to compute a correlation coefficient. This coefficient is indicated using R and is a number that encodes the normalized strength of the linear relationship between two variables. The normalization imposes boundaries of -1 to +1. Negative, 0, and positive correlation coefficients have distinct interpretations. So, R between 0 and 1 indicates a positive relationship, meaning both variables increase and decrease together, like in the death metal example above. R equals 0 indicates no linear relationship, meaning that you cannot predict the value of one variable based on the other. Now, the linear qualification is important because nonlinear relationships can exist in variables with r equals 0. More on this later. For r values between -1 and 0, this indicates a negative relationship, which means that one variable increases when the other decreases. As the magnitude of r increases, that is, gets further from 0, the strength of the relationship increases. Figure 12.2 shows several examples of correlations with different magnitudes and signs. This paragraph references figure 12.2, which shows examples with different correlation values. So this figure shows a 3x3 grid of subplots. So there are 3 rows and 3 columns. In the top row, we see linear relationships with r equals 1 on the left, r equals 0.71 in the middle, and r equals 0.13 on the right. The r equals 1 panel shows all of the dots exactly on the same line, so a perfect relationship. R equals 0.7 in the middle shows the dots strongly linearly related to each other. That's visibly obvious, but they are in a bit of a cloud here, so there's some variability. And for r equals 0.13, it's not really clear that there is a visual relationship between the x and y axes. We just see a cloud of dots. Okay, then we have the lower panel. I'll get to the middle panel in a moment. The lower panel shows on the left r equals minus 0.21, and there we see a roughly looking like a cloud of dots. There does appear to be some negative relationship. In the middle, we have r equals minus 0.73. There's a clear negative relationship, so when the x-axis values are high, the y-axis values are low, and vice versa. And then on the right, we have r equals -1. Here again, we see a perfect relationship. All of the dots are on a line, but now this line is going down, sloping down instead of sloping up, as was the case with the positive correlation. Okay, then the interesting cases are in the middle panel. And here we see all 3 panels in the middle row have r equals 0.00. In the left, we see all the dots arranged in a perfect circle. In the right, the dots are arranged in a U. And in the right, the dots are arranged in an X pattern. So all of these cases show very strong relationships between the X and Y axis, but they are non-linear relationships, and the linear components of these relationships are 0. Back to the text. Here are a few additional points to know about a correlation coefficient. Point 1, statistical significance. The R value is a descriptive statistic of a sample, and you cannot determine its statistical significance simply from its magnitude. Instead, you need to apply an inferential statistical test to compute a p-value associated with the R value. The statistical significance depends on the correlation coefficient and the sample size, and therefore R equals 0.2 could be statistically significant or non-significant depending on the sample size. I'll show the formula to compute the p-value later in the chapter. Point 2, limited to linearity. You will see in the next section that the math underlying the correlation coefficient comprises linear operations, which means that the correlation coefficient can detect only the linear component of a relationship. And that's what I was illustrating in the middle row of figure 12.2 that I described a moment ago. Point 3, causality. A correlation coefficient does not demonstrate a causal relationship between the variables. You can find myriad funny examples of this by searching online for, quote, funny examples about correlation and causality, end quote. My personal favorite is the negative correlation between the number of pirates and the global average temperature, implying, incorrectly, that a pirate shortage has caused global warming. Now, to be clear, funny correlations like this are not mathematically incorrect, nor are they artifacts. They indicate true relationships in the data. The problem comes from mistakenly believing that there is a causal relationship between the variables. Over the past several decades, the number of pirates has decreased and the global average temperature has increased. Each variable is independently related to the passage of time while being unrelated to each other. This causality fallacy can have serious consequences when incorrectly applied, such as interpreting a correlation between marijuana use and psychopathy indicate that marijuana causes mental health problems, when the alternative interpretation, so people with mental health problems are more likely to self-medicate, is an equally valid interpretation of this correlation. Ultimately, proper experimental methods are required to establish causality. Point 4. Terminology. A minor but germane point. Sometimes people say that there is, quote, no correlation, end quote, between two variables. In fact, there is always a correlation between paired variables. That correlation coefficient might not be statistically significantly different from 0, but it still exists. So the correct phrasing is, quote, no significant correlation, end quote. It's a minor and forgivable sloppiness, but not one that you will ever make. Best fit line. There is a misconception that the correlation coefficient is the slope of a best fit line in a scatter plot of two variables. Figure 12.3 shows that this is not the case. The correlation coefficients in the two data sets are the same, while the slopes of the best fit lines differ by an order of magnitude. The best fit line through a cloud of data is a relevant and interpretable statistic, and it's one that you can calculate with a regression analysis. You'll learn more about regression in Chapter 15. I bring this up here only to make sure you do not confuse the two concepts. This paragraph references Figure 12.3, which shows that two data sets can have the same correlation but different slopes of the best fit line. So in panel A, we see a cloud of data. Actually, both panels show clouds of data. Panel A, the title is Slope equals 0.35, R equals 0.67. And in panel B, the slope is 2.97, and the R value is exactly the same, 0.67. Section 12.2, Covariance and Correlation Formulas. To understand the math of the correlation coefficient, it helps first to learn the math of covariance. You can think of a correlation as the normalized covariance, or you can think of covariance as the non-normalized correlation that preserves the units of the data. Section 12.2.1, Covariance. Covariance has different numerical values from correlation, unless the data are Z-normalized first, more on this point later. But the interpretation of the sign is the same as with the correlation. Negative covariance indicates that one variable goes down when the other goes up. Positive covariance indicates that both variables go up and down together. And zero covariance indicates that the variables have no linear relationship. To introduce the formula, imagine that we have a group of first-year university students and we measure their performance on a history exam and a statistics exam. We can compute the covariance between the exam scores to quantify their linear relationship. I'll use H to indicate scores on the history exam and S to indicate scores on the stats exam. Each student will be indicated using the subscript I, so H sub I is the history exam score of the ith student. There are n students in our sample, and C is the covariance between them. Equation 12.1. C equals 1 over n minus 1 times the sum from I equals 1 to n of the quantity of the product of two terms. The first term is h sub I minus h bar. The second term is s sub I minus s bar. So let me try to rephrase that. So we have the covariance equals 1 over n minus 1 times the sum over all of the elements in the set from I equals 1 to n of the product of the demeaned or mean-centered h sub I value by the demeaned s sub I value. Back to the text. For clarity and connection with later sections on correlation and covariance matrices, I'm going to rewrite equation 12.1 using demeaned variables. So here we have equation 12.2, which reads C equals 1 divided by n minus 1 times the sum from I equals 1 to n of h sub I tilde times s sub I tilde, where h sub I tilde is h minus h bar, and s sub I tilde is s minus s bar. Back to the text. Equation 12.2 says that we multiply each student's history exam score by their stats exam score, sum over all the students, and then divide by the number of students minus 1. A few comments on this equation. Comment 1. The variables must be mean-centered before computing the covariance. That ensures that the sign of the covariance matches the relationship between the variables. Imagine leaving out that step. Exam scores are strictly positive, and so a negative relationship between history and stats exam scores would still yield a positive covariance. On the other hand, when variables are mean-centered, students who score below the mean in history but above the mean on stats will contribute a negative number to the summation. Comment 2. The covariance is scaled by n minus 1. The reason for scaling is to prevent the covariance from trivially increasing with sample size. In other words, scaling changes the sum to an average. You might have initially expected to scale by 2 times n minus 1 because there are 2 variables and 2 sample means. But the quote-unquote statistical atom here is a pair of data points, not an individual data point, and there are n pairs. Comment 3. There is only one n term. There isn't a separate n sub h and n sub s. Covariance and correlation require a pair of variables that have the same size and that come from the same subjects. In this example, you can correlate history and stats exam scores in the same students, but you cannot correlate history scores in one group of students with stats scores in a separate group of students. Comment 5. The unit of covariance is the product of the units of the individual variables. If both variables have the same units, then the covariance units might be interpretable. So one example is in multi-channel time series signals, where the covariance between 2 channels could have units of squared volts. In many cases, though, the units are not easily interpretable. In our example here, the unit of C is history scores times stat scores, although it would be incorrect to call it squared scores if the scores are incomparable. For example, if the history exam is graded 0 to 100, while the stats exam is graded 0 to 10. So, for many applications of the covariance, units are not interpretable and therefore ignored. Comment 5. If you are familiar with linear algebra, then you'll recognize equation 12.2 as the dot product between the 2 data vectors. Indeed, C equals H transpose S, assuming mean centering and scaling by n minus 1. Comment 6. Covariance is linear because it involves only scalar multiplications and summation. This is why covariance can assess only the linear component of a relationship between 2 variables. Comment 7. Scalar multiplication is commutative, meaning that the covariance between history scores and stat scores is the same as the covariance between stat scores and history scores. In other words, C equals H transpose S equals S transpose H. This symmetry is the reason why you cannot infer causality from a covariance or correlation analysis. Comment 8. Don't worry about the statistical significance of a covariance. Statistical significance is used for a correlation. It is possible to calculate statistical significance of covariance using permutation testing, which you'll learn about in the exercises of Chapter 16. Here's a quick numerical example of the covariance between history and statistics exam scores in 4 students. Here we have a series of equations with the history exam scores being 74, 63, 58, and 70. And the stats exam scores as variable S is 4, 7, 2, 9. You can see they are completely on different scales. In the next set of equations, I've printed out the mean-centered variables and the covariance, which is the sum of the element-wise product divided by 3, because there are 4 scores, 4 students, and the final covariance score is C equals 8.5. Back to the text. Although the number 8.5 on its own is difficult to interpret, the positive sign of the covariance indicates that students who do well on history exams are likely to do well on statistics exams. Section 12.2.2, Autocovariance. What happens when you compute the covariance of a variable with itself? Let's find out by rewriting equation 12.1. To make this more general, I'll name the variable x. Here we have equation 12.10, which reads C equals 1 over n minus 1 times the sum from I equals 1 to n of the product of 2 terms. We have xi minus x bar times itself, xi minus x bar. This is rewritten in equation 12.11, which reads C equals 1 over n minus 1 times the sum from I equals 1 to n of xi minus x bar, that quantity squared. Back to the text. Remarkably, we've arrived at the exact same formula as variance. That was equation 4.5. This means that the covariance of a variable with itself is simply the variance of that variable. This is the key insight that allows us to transform a covariance into a correlation. Margin note. I hope that this discussion also helps you understand why a covariance is scaled by n minus 1 and not 2 times n minus 1. Section 12.2.3, Correlation. The numerical covariance value is difficult to interpret because it retains the units of the 2 variables. Consider, for example, that the covariance between height and weight has units centimeters times kilograms. Footnote. If you think you can interpret it, you're probably thinking about centimeters by kilograms. This is centimeters times kilograms. Back to the text. To make matters even more confusing, the covariance value between height and weight, measured as centimeters and kilograms, is numerically different from the covariance value in the same data but measured as pounds and inches, although the statistical relationship between these variables is the same. Therefore, a more interpretable measure of a linear relationship would involve normalizing out the scale and the units of the data. There are 2 ways to apply such a normalization. Normalize the data before computing covariance, or normalize the covariance value. Let's start with the latter. This normalization involves scaling the covariance by the square root of the product of the variances of each variable. I will use variable names x and y. Equation 12.12. R equals the fraction of, in the numerator, the sum from I equals 1 to n of the product of 2 terms x sub I minus x bar and y sub I minus y bar. In the denominator, we have the square root of the product of two terms. First term is the sum from I equals 1 to n of x sub I minus x bar, that quantity squared. And the second term is the same summation, but with y sub I minus y bar squared. Back to the text. Equation 12.12 is known as the Pearson correlation coefficient. I have several remarks about this equation, but first I want you to see two alternative ways to write it. In the equations below, assume that the variables are already mean-centered. In other words, x bar equals y bar equals 0. So here we have equation 12.13, which reads r equals fraction of the numerator being the sum over x sub I times y sub I. And in the denominator, we have the square root of two terms, the sum of x squared and times the sum of y squared. And that can be rewritten as another fraction. In the numerator, we have x transpose y, and in the denominator, we have the square root of x transpose x times y transpose y. Back to the text. Now for some remarks. Remark 1. The division by n-1 is missing. However, that normalization term would appear once in the numerator and twice in the denominator as a product under the square root. Therefore, it cancels out and is excluded for simplicity. Remark 2. The correlation coefficient has no units because the units cancel in the fraction. You can work this out for yourself by thinking about x being weight in kilograms and y being height in centimeters. Remark 3. Consider that the maximum possible value of r would occur when x equals y, in which case the numerator and denominator are equal, which means r equals 1. Conversely, the minimum possible value occurs when x equals minus y, in which case r equals minus 1. Remark 4. As you now know, the covariance of a variable with itself is its variance. The correlation of a variable with itself is trivially r equals 1. This is also the variance of a z-standardized variable, which is something to pin in the back of your mind for a moment. Remark 5. A potential source of terminological confusion. There is an analysis called autocorrelation, which is the correlation of a time series variable with a temporally shifted version of itself, and which is used to quantify rhythmicity in a time series. It's an analysis you would come across in a signal processing book and is not further discussed here. Remark 6. Equation 12.12 is not defined when the variance is 0. This means that a correlation coefficient requires variability in the data. Covariance is not burdened by this constraint. Remark 7. There are several kinds of correlations that have different formulas, and you will learn two other correlations, Spearman and Kendall, later in this chapter. However, the Pearson correlation is the most commonly used, so if you read or hear only the term correlation without a preceding modifier, you can assume it refers to the Pearson correlation. Remark 8. Correlation coefficients between different pairs of variables can be distinguished using subscripts. For example, the correlation between x and y can be distinguished from the correlation between x and z using r subscript xy and r subscript xz. End of remarks. Finally, let's think about what would happen if you normalized the data instead of normalizing the covariance. Remember that z-scoring involves mean centering and variance normalizing. Mean centering is already part of the covariance and correlation formulas. When you standardize the data to ensure that each variable's variance equals 1, then the denominator of equation 12.12 will also be 1. So this implies that the Pearson correlation coefficient is equivalent to the covariance when both variables are z normalized. Now, this statement is not true if only one variable is z normalized. So, you can normalize the data or you can normalize the covariance, but the conclusion is the same. The correlation coefficient is the variance normalized covariance. Section 12.3, Correlation Matrix. All the formulas so far in this chapter involved two variables. What if you have a data set with three variables? Correlation is fundamentally a bivariate measure, which means that it is limited to two variables. However, you can compute the correlation coefficient among all pairs of variables. A data set with three variables has three unique correlation coefficients, excluding the trivial correlation of a variable with itself. And in general, a data set with m variables contains the quantity m squared minus m divided by two unique correlations. The set of all bivariate correlations in a data set can be organized into a correlation matrix. In a correlation matrix, the element in each row and each column is the correlation between the corresponding variables. Of course, the diagonal elements are all trivially r equals 1. This paragraph references figure 12.4. Figure 12.4 shows a correlation matrix for a three-variable data set. The diagonal elements are all 1, and the off-diagonal elements are symmetric across the main diagonal, going from the top left to the bottom right. So we see in the figure a 3x3 grid where the three rows and three columns are all labeled X, Y, and Z. The diagonals are 1s, indicating a correlation coefficient of 1, and the off-diagonal elements have R with a subscript corresponding to the two variables that are being correlated. So, for example, the element in the second row and first column is R sub YX. And then the element in the first row and second column, which is across the diagonal from the element I just described, is R sub XY. Back to the text. Because a correlation matrix includes the pairwise correlations amongst all pairs of variables, a correlation matrix requires all variables to be measured from the same subjects, just like with any correlation. Correlation matrices are usually indicated using a boldface capital R, and covariance matrices are usually indicated using a boldface capital C. If the dataset has a small number of variables, the elements in the matrix can be shown as numbers. This is not scalable to larger datasets, and therefore the correlation matrices are visualized using a pseudo-color mapping of correlation value. This paragraph references figure 12.5, which shows the visualization of a correlation matrix. It is a grayscale heat map with 20 rows and 20 columns, and the color intensity at each grid location in this matrix corresponds to the correlation coefficient between the corresponding pairs of data features. We also see that the diagonal is all white, the maximum value of color saturation, indicating that the correlation of each variable with itself is 1. Back to the text. A correlation matrix might seem like a waste of space. Indeed, all correlation values appear twice, and showing the diagonal elements is just gratuitous. However, this matrix is key to unlocking decomposition such as principal components analysis. It also results from the linear algebra approach to computing covariances and correlations. Section 12.3.1 Linear Algebra. If you have no background in linear algebra, you might find this section confusing. If so, I apologize, but assure you that it is not critical to understanding correlation matrices. Let's imagine a dataset X of size n by m, which comprises n rows of observations and m columns of data features. To simplify the formulas, let's assume that each column is demeaned and all data are divided by n-1. The set of all pairwise dot products between columns can be written compactly as C equals X transpose X. This is equation 12.4, C equals X transpose X. Working through the matrix sizes, you'll see that the size of the product matrix C is M by M, or features by features, and that each element, C sub I comma j, is the dot product between the ith and the jth data feature. You'll also appreciate that C must be symmetric because it is graded as the product of a matrix with its transpose. Let's create a diagonal matrix sigma in which the ith diagonal element is the standard deviation of column I. Then we can transform between covariances and correlations as follows. Here we have equation 12.15, which reads R equals sigma inverse times C times sigma inverse, which equals sigma inverse times X transpose times X times sigma inverse. So that's the definitions for R based on C, the covariances, and based on the diagonal matrix of standard deviations. And then we have equation 12.16, which states C equals sigma R sigma. This is the way to compute the covariance matrix from the correlation matrix. You will get to explore these matrices in the exercises. Section 12.4, Correlations in Code. There are several ways to compute the correlation coefficient in Python or R. You won't be surprised that in the exercises, I will give you the opportunity to code the formula for the correlation coefficient yourself. But in practice, you can use the NumPy or SciPy libraries in Python or the core function in R. The following Python code will compute the correlation between variables x and y, assuming both variables are NumPy arrays. I'll get to the R code at the end of this section. So here we have some code. Using SciPy, its variable name equals stats.pearsonr, with the two inputs being x, comma, y. And the next line of code is variable using NumPy equals np.corecoef inputs x, comma, y. The outputs, however, are different. SciPy's output looks like this. We have the object Pearson R result with two elements, statistic equals 0.876, and p-value equals 10 to the minus 17. While NumPy's output looks like this. Here we have a matrix, a NumPy array, comprising four numbers. The first row is 1.876, and the second row is 0.8761. In other words, SciPy returns a tuple containing the correlation coefficient and its p-value, while NumPy returns the correlation matrix without p-values. One implication of this difference is that SciPy's correlation function requires two vector inputs, whereas NumPy's correlation function can take a matrix as input. Consider the following code. Here we have variable x equals numpy.vstack, x none comma all, y none comma all. Next line is using SciPy equals stats.pearsonrx with a comment that says nope. And the next line is variable using NumPy equals numpy.corecoef x. In other words, I created a matrix, a NumPy array, variable x, by horizontally stacking the variables containing vectors x and y. In the SciPy.stats function Pearson R, this produced an error, and in NumPy's function corecoef, this gave a valid result. Back to the text. This code will actually crash on the stats.pearsonr line because SciPy does not accept a data matrix as input if that matrix is a NumPy array. The subsequent line, however, does work and returns the same matrix that I showed above. Annoyingly, NumPy's core function does not compute p-values. So, if you want a matrix of correlation coefficients with their associated p-values, you have three options. Option 1, use the SciPy correlation function in a double for loop. Option 2, implement the p-value computation on your own. This is presented in exercise 3. Or option 3, input a pandas data frame instead of a NumPy array. This is explored in exercise 10. In R, you can obtain a correlation coefficient using the following code. R equals core with inputs x, y. The result is just the coefficient, not its associated p-value. To obtain a p-value, you can use the function core.test. So core.test, input x, y, returns an object that reads Pearson product moment correlation. Data x and y. T equals 11.4, df equals 98, p-value less than 2 times 10 to the minus 16. Alternative hypothesis, true correlation is not equal to 0. We have a 95% confidence interval and the sample estimate of the correlation coefficient of 0.75. You can extract the statistical quantities from the output of core.test using the following code. R result equals core.test x, y, and then we have R result $statistic gives the t-value, R result $estimate gives the coefficient, and R result $p.value gives the p-value. You can compute a correlation matrix in R by entering a data frame into the core function. So here we have df equals data.frame, x equals x, y equals y, and then the function core with input df. This returns a 2x2 matrix with 1s on the diagonal and 0.75 on the off diagonal. Section 12.5, Assumptions of Correlation. The assumptions listed below are for the Pearson correlation coefficient. Depending on the nature and severity of the violation, these issues can be dealt with through better data cleaning or through non-parametric correlation methods such as Spearman or Kendall. Assumption 1, data type. The Pearson correlation is appropriate for interval or ratio data. If you have ordinal data, so sortable or discrete, you can use the Kendall correlation. Assumption 2, linear relationship. As I illustrated in figure 12.2, a Pearson correlation will identify only the linear component of a relationship between two variables. Any nonlinear relationships between the variables are not identified. Violations of this assumption can be addressed using a Spearman correlation or through data transformations. In fact, the Spearman correlation is simply the Pearson correlation applied to rank transform data. More on this point later. Assumption 3, normality. Each variable should be roughly normally distributed. The reason for this assumption is that the mean and variance are used in the computation, and so the correlation coefficient is only meaningfully interpreted if the mean and variance are suitable characteristics of the data. You will see the impact of violating this assumption in the discussion of Simpson's paradox later in this chapter. Violations of this normality assumption can be addressed using subgrouping or using a Spearman or Kendall correlation, depending on the nature of the data. Assumption 4, homoscedasticity. Homoscedasticity means that the variance is comparable at all values. Refer back to figure 16 in chapter 4 if you need a refresher. Violation of this assumption does not necessarily invalidate Pearson correlation coefficient. However, strong heteroscedasticity indicates that the strength and nature of the relationship depends on the values of the variable. There are two solutions to strong heteroscedasticity. First, you can transform the data, for example, using a log or square root transformation. Or second, you can perform a subgroup analysis in which you compute the correlation coefficient separately for different ranges of the data that have comparable variances. Assumption 5, independence. This means that each pair of observations is not influenced by or related to other observations in the dataset. Dependencies across observations can bias the estimate of the correlation strength. A typical example is time series correlations, in which each time series has strong autocorrelations. Alternative measures for time series correlations in the presence of autocorrelation includes ARIMA and coherence analyses, but these kinds of analyses are not discussed here. Assumption 6, no outliers. Outliers can have severe consequences for correlations for the same reason that outliers have consequences on other parametric statistical analyses. You'll see an example of outliers impacting the correlation coefficient later in this chapter in the demonstration of Anscombe's quartet. Solutions include data cleaning, Spearman correlation, and permutation testing. Section 12.6, Simulating Correlated Data. There are several ways to create a dataset with correlated data features. In this section, I will introduce you to 3 methods. The easiest and least effort method involves setting one variable equal to another. This would impose r equals 1, and then adding some noise to decrease that correlation. In the equations below, eta is a noise factor. Here we have 3 equations. Equation 12.17 reads x is distributed according to standard normal distribution, so Gaussian distribution, with a mean of 0, standard deviation of 1. The next equation is y tilde is distributed also as standard normally distributed numbers. And then we have equation 12.19, which reads y equals x plus y tilde times eta. Back to the text. Corresponding code would look like this. In Python, we have x equals numpy.random.rand 50, and y equals x plus numpy.random.randn length of x times 1. And in R, we have x equals r norm 40, and y equals x plus r norm, the length of x times 1. Back to the text. With eta equals 1, x and y will correlate at around r equals 0.6. The disadvantage of this method is that the exact correlation value is not easy to control. This brings us to the next method, which works by drawing random numbers from a population with a specified correlation strength. Here we have 3 equations. Equation 12.20 reads x is distributed according to a standard normal distribution. Y tilde is distributed according to also a standard normal distribution. And then we have equation 12.22, which reads y equals x times r plus y tilde times the square root of the quantity 1 minus r squared, where r is the population correlation coefficient. Notice that x and y are independent when r equals 0, and that x equals y when r equals 1. In finite samples, the empirical correlation won't match exactly the specified population correlation r due to noise and sampling variability. Larger samples will have more accurate estimates, analogous to how x bar should be close to mu when drawing random numbers from normal distribution with a mean of mu and standard deviation sigma squared. This is a common method for simulating correlated data, and you'll use it often in the exercises in this chapter and in later chapters. The third method for creating correlated variables is an extension of equation 12.22 to the multivariate case. The details of the method involve a Cholesky decomposition of a covariance matrix with added measures in case the decomposition is not possible. I won't get into the math here, but it is implemented by providing a population covariance matrix to dedicated Python or R functions. For example, the following code will create a 50 by 2 data matrix in which each variable has a variance of 1 and the two variables covary at 0.4. Setting the means of both variables to 0, that's the first input, and setting their variances to 1, that's the diagonal terms in matrix C, means that the covariance matrix will approximately equal a correlation matrix, and is only approximately because of sampling variability. So here we have Python code that's variable C equals numpy.array, and I'm inputting a matrix with the first row being 1, 0.4, and the second row being 0.4, 1. Then we have x equals numpy.random.multivariate_normal, and then the first input is a list 0, 0. The second input is the covariance matrix C, and the third input is 50. Then we have the R code. Here we import the library mass, all in capital letters, MASS. We define C to be a matrix of elements 1.4.41 with 2 rows, and we organize by row equals true. And then we have x equals MVR norm with inputs n equals 50, mu equals 0, 0, and sigma equals C. Section 12.7 Non-Parametric Correlations. The idea of non-parametric correlations is the same as that of the Pearson correlation. Quantify the relationship between two variables, but the implementations are modified to suit data that violate the assumptions discussed in section 12.5. Section 12.7.1 The Problem with Pearson. Apologies for the clickbait, although alliterative, title. There is no problem with the Pearson correlation, but the Pearson correlation coefficient can be difficult to interpret if the data violate the assumptions discussed in section 12.5. In particular, the Pearson correlation can over or underrepresent relationships if they contain nonlinearities or outliers, or if they are drawn from strongly non-Gaussian distributions. This is nicely illustrated using Anscombe's quartet, which is a series of data pairs that have identical Pearson correlation coefficients but strikingly different relationships. An even more striking example is called the Datasaurus dozen, which I won't show here because it's an animation, but you can find it online with a quick internet search. This paragraph refers to figure 12.6, which shows Anscombe's quartet. This is a set of relationships that highlights how the Pearson correlation coefficient can be difficult to interpret in the presence of nonlinear relationships or outliers. This figure shows a 2x2 grid of panels, with each panel being a scatter plot. So we have the top left scatter plot shows R sub P equals 0.82 and R sub S equals 0.82. So R sub P is the Pearson correlation, R sub S is the Spearman correlation. This data set shows normally distributed numbers with a linear relationship, and so the Pearson and Spearman correlation coefficients are the same. In the top right scatter plot, we have a nonlinear relationship. So it goes up and then it starts going down at something like part of a quadratic relationship. Here we have, again, the Pearson correlation is 0.82. The Spearman correlation is 0.69. In the lower left panel, we have what looks like nearly a perfect linear relationship, except for one outlier in the second to last data point. It's much higher than the other data values. Again, the Pearson correlation is 0.82. The Spearman correlation is 0.99. Finally, we have the lower right panel where all of the data points are perfectly vertically aligned except for one very strong outlier all the way to the right, and that produces a Pearson correlation of 0.82, again, but a Spearman correlation of 0.5. Back to the text. Section 12.7.2, Spearman. Spearman is a non-parametric alternative to the Pearson correlation and is designed to eliminate the impact of outliers. Computing the Spearman correlation is simple. First, rank transform each variable, then apply the Pearson correlation to the ranked data. It's that simple. Margin note. Spearman correlation is often indicated using rho, the Greek letter rho, or R sub S to disambiguate it from the Pearson R. Back to the text. Interpretation. The rank transform obviously eliminates outliers, but it has two other consequences. Monotonic nonlinear functions become linear, and distances are equalized. That is, the ranked distance between 1.1 and 1.2 is the same as the ranked distance between 1.1 and 12. Thus, the interpretation of the Spearman correlation is different from that of the Pearson correlation. Whereas the Pearson correlation measures the linear relationship between two variables, the Spearman correlation measures the monotonic relationship between two variables. Monotonic means that they go up and down together, but the changes could be linear or nonlinear. It's a subtle but impactful difference. Does the difference in interpretation between Pearson and Spearman matter? This depends on the nature of the hypothesis and the required precision of the interpretation. Consider the relationship between height and age during the first 20 years of human development, in which height increases monotonically but non-linearly. A strict interpretation of a positive Pearson correlation coefficient would imply that people continue to grow at the same rate from birth to 20 years old, whereas a Spearman correlation simply implies that at any age, people are likely to be taller than they were when they were younger. Although technically a logarithmic growth curve is the most appropriate way to fit the data, the Spearman correlation provides a more accurate description than the Pearson correlation. So, why not always use the Spearman correlation if it is more general than Pearson? There are 3 reasons to prefer Pearson over Spearman. Reason 1, preservation of information. The rank transform is lossy, which means that the Spearman correlation entails loss of information. Potentially meaningful variability that contributes to the Pearson correlation might be lost or altered in the Spearman correlation. Reason 2, sensitivity. For the same reason as above, Pearson's correlation can be more sensitive to subtle relationships between variables. Reason 3, interpretability. Pearson's correlation can be easier to interpret because it indicates a linear relationship. Monotonic relationships are less precise because the nature of the relationship is not necessarily clear or easy to interpret. The conclusion is that you should use Pearson when the data meet the assumptions and use Spearman when violations of those assumptions justify a non-parametric test. Section 12.7.3, Kendall's correlation for ordinal data. Kendall's correlation is appropriate for data that are sortable and discrete. Recall that the Pearson correlation is appropriate for interval or ratio data and not for ordinal data. If you have ordinal data, Kendall is your go-to correlation method. Margin note. Kendall correlation is often indicated using the Greek letter tau. Thus, use R for Pearson, rho for Spearman, and tau for Kendall. Back to the text. Many applications of the Kendall correlation involve subjective ratings, such as online product ratings or ranking of preferences for sports players or music bands. Kendall's correlation is not based on dot products and variances like Pearson and Spearman are. Instead, Kendall works by comparing the number of concordant and discordant pairs of data. A concordant pair is two pairs of data points, x1 and y1, and x2 and y2, such that if x1 is greater than x2, then y1 is greater than y2. Or if x1 is less than x2 and y1 is less than y2. And a discordant pair is such that x1 is greater than x2 while y1 is less than y2. These inequalities make Kendall non-parametric. It doesn't matter if x2 is only slightly bigger or stupendously bigger than x1. In the equation below, C is the number of concordant pairs and D is the number of discordant pairs. This is a simplified version of Kendall's tau. Here we have equation 12.23. Tau equals the fraction with the numerator C minus D and the denominator C plus D. Back to the text. Let's think about this equation. If all data pairs are concordant, so D equals 0, then the equation reduces to C over C equals 1. On the other hand, if all data pairs are discordant, then we get minus D over D equals minus 1. And if there is an equal number of concordant and discordant pairs, then we get tau equals 0. This indicates that the Kendall correlation has the same bounds and the same interpretation as the Pearson correlation. In practice, a modified version of equation 12.23 is used, which accounts for ties in the data. That equation is called Kendall's tau sub b, also written tau dash b, and is implemented in the Python function Kendall tau in the scipy.stats library and using the input method equals Kendall in the core function in R. Example. Remember the research question about whether death metal preferences are familial? Let's go back to that example. I asked ChatGPT to create humorous names for death metal bands, and then I created some ranked preferences for 5 pairs of siblings. These are fake data, but they would result from asking a sibling pair to rank order their preference of the bands. The raw data and the scatter plot are shown in figure 12.7. Figure 12.7 refers to a scatter plot showing an example of Kendall correlation in an imagined dataset of death metal band rankings. On the left, we have a scatter plot with the x-axis corresponding to brothers' ratings and the y-axis corresponding to sisters' ratings. And we have 5 data points illustrated in this graph with a tau of 0.4. And here are the funny band names that ChatGPT came up with. We have Zombie Zucchini Zephyr, Vampiric Vegetarians, Demonic Dishwashers, Satan's Fluffy Bunnies, and Unicorn Apocalypse. Section 12.8, Statistical Significance. There are 2 ways to determine the statistical significance of a correlation coefficient: t-statistic and permutation testing. With both approaches, the null hypothesis is that there is no linear relationship between the 2 variables. In other words, H0 is R equals 0. The alternative hypothesis states that the correlation coefficient is non-zero. In other words, HA is R is not equal 0. Permutation testing involves creating an empirical H0 distribution by repeatedly shuffling the mapping between the 2 data features without altering the data features themselves. This will be covered in Chapter 16. A t-value is calculated from the correlation coefficient using the following formula. Here we have equation 12.24, which reads t sub n minus 2 equals a fraction with the numerator being r times the square root of the quantity n minus 2, and the denominator is 1 minus r squared. Back to the text. Under the null hypothesis, this t-value is distributed with the same t-distribution that you learned about with t-tests. Thus, you compute the p-value as the probability of observing a t-value at least as extreme as your observed t-value using n-2 degrees of freedom. Importantly, notice that the numerator of the t-value includes the sample size. This means that a given correlation coefficient is more likely to be significant with larger sample sizes. This is illustrated in figure 12.8, which shows that the t-value increases when the correlation strength is held constant while the sample size increases. This should make sense intuitively. With larger samples, our confidence in the result increases, even if the strength of the relationship is the same. This paragraph refers to figure 12.8, which shows the relationship between the correlation strength, the sample size, and the t-value. The figure shows a heat map with sample size on the x-axis ranging from around 10 to around 500, and correlation strength on the y-axis ranging from 0.1 to 0.8. And the color axis, which is actually grayscale, goes from 2 to 10, and that indicates the t-value. And what you see is a nonlinear relationship between sample size and correlation strength. So, for example, a given correlation of 0.5 is going to have a small t-value when the sample size is small, but a larger t-value when the sample size is large. Section 12.8.1 Fisher-Z transformation. The procedure described above shows how to evaluate the statistical significance of one correlation coefficient. Sometimes you have many correlation coefficients, and you want to know if the sample of correlations is significantly different from zero. This happens, for example, in psychology research, where you compute correlations between two variables within each individual, and then you want to know whether that relationship is consistently positive or negative across your sample of research participants. A sample of correlation coefficients is drawn from a uniform distribution. Coefficients cannot be less than -1 or greater than +1. This means that a sample of correlation coefficients violates the assumption of normality required for a parametric t-test. A solution to this problem was proposed by Fisher and involves applying the following transformation to the correlation coefficients. Here we have equation 12.25, which reads z sub f, so z for f Fisher, equals 1/2 times the natural log of the fraction 1 plus r over 1 minus r. And that is the same as the inverse hyperbolic tangent function of r. Back to the text. The result of the Fisher transform is often called z, just z on its own. But this is not the same as the standard deviation value that you would get from a z-score transform. If there's a risk of confusion, you can use z underscore f, r underscore z, or capital F in parenthesis r. This transformation has little impact on values close to 0, while stretching values closer to the absolute value of 1. Figure 12.9 shows the impact of applying this transformation. In this case, I did not actually simulate correlation coefficients, but instead just drew numbers at random from a distribution that follows a uniform distribution between -1 and +1. This paragraph refers to figure 12.9, which shows the impact of the Fisher-Z transform. We have two panels here. Panel A shows histograms of uniform random data and its Fisher transform, shown in two different colors overlapping. And you can see that the R values are uniformly distributed between -1 and +1. And after applying the Fisher-Z transform, it appears quite a normal distribution ranging from around -3 to +3 or so. And then in panel B, we have a scatter plot of the raw correlation values versus the Fisher transformed correlation values. And what you see is that it has kind of a inverted S-shaped pattern where R values close to -1 have a steep decline on the y-axis, so very strong negative values for the Fisher-Z transform. And then there is a region from approximately -0.5 to +0.5, where the transformation appears to be quite linear, visually almost perfectly linear. And then as the R values get closer to +1, the Fisher-Z transform values shoot up to larger and larger values. Back to the text. How necessary is this transformation in real data? The thing is that the nonlinearity has little impact on values close to 0, and empirical correlations are not often so close to 1 in research areas that involve noise or complex systems. So I repeated the simulation shown in figure 12.9, but instead of drawing coefficients randomly from a uniform distribution, I simulated a dataset with 45 uncorrelated variables and computed all intervariable correlation coefficients. This sample of null hypothesis correlation coefficients is close to 0, and therefore were minimally impacted by the Fisher transform. These two demonstrations show that the two extremes of the impact of the transformation, that is, negligible impact when R is close to 0 and big impact when R is close to the absolute value of 1, the impact on real correlation coefficients will be somewhere in between. Nonetheless, it's a good habit to apply the Fisher-Z transform to correlation coefficients if you are using them in a parametric analysis like a t-test or an ANOVA. This paragraph references figure 12.10, which is the same as figure 12.9 that I just described, but using correlation coefficients created under the null hypothesis by correlating pairs of random numbers. So here we see in panel A, the two histograms for the raw correlations and the Fisher-Z transform correlations are not exactly but nearly overlapping distributions. They appear roughly normal. And then in panel B, in the scatter plot of the raw correlations by the Fisher-Z transformed correlations, we see again that the relationship from R minus 0.3 to R plus 0.3 approximately appears to be almost perfectly linear. Section 12.9, the subgroups correlation paradox. Although I appreciate and agree with the practice of naming mathematics concepts after their inventors, there are times when this convention impedes comprehension and memory. In this section, I will introduce you to what is formally called Simpson's paradox, although I think of it as the subgroups correlation paradox. Simpson's paradox occurs when there appears to be a correlation in a data set, when in fact the data comprise distinct subgroups that have mean offsets. I believe that this paradox is self-evident from inspecting figure 12.11. Figure 12.11 shows an example of Simpson's paradox in which subgroups show negative correlations while the total sample has a positive correlation due to mean offsets. So this figure illustrates a scatter plot, and there are three clusters of data. There are dark gray squares, there are middle gray circles, and there are light gray triangles. And what you see is that the dark gray squares are clustered in the lower left, the middle gray circles are in the middle, and the light gray triangles are in the upper right. Now, within each group, there is a negative correlation. And in fact, that negative correlation is statistically significant for two of the three groups, but the magnitudes are minus 0.3, minus 0.5, and minus 0.6. So within each subgroup, there is a negative correlation. However, because of the mean offsets, the total correlation, when ignoring subgroups and just pooling all of the data together into one analysis, that correlation coefficient is 0.7, and it is highly statistically significant. Back to the text. How do you check whether Simpson's paradox might explain your correlation results? Visual inspection of your correlation using scatter plots is a great method. This is not always feasible. For example, if your study involves computing dozens or hundreds of correlations. In this case, you could check the data for normality using the methods discussed in section 11.1.9, or you could define subgroups based on some data feature. But the best way to check for Simpson's paradox is to use domain knowledge about your data set to consider that there might be distinct subgroups. For example, perhaps the three groups in figure 12.11 correspond to different patient groups or different age ranges, different countries or car manufacturers or economic sectors, and so on. If there are subgroups in your data, you can run the correlation analysis separately for each subgroup and interpret the results accordingly. Section 12.10, Cosine Similarity. Cosine similarity is a measure used in machine learning to assess the relationship between two variables. The name sounds really cool, like it's related to geometry and some weird high-dimensional spaces, but it turns out that it's closely related to Pearson's correlation coefficient. Before discussing how cosine similarity is similar to and different from the Pearson correlation, I would like you to inspect the formulas for the correlation coefficient and cosine similarity and ponder the circumstances under which they would be the same or different. Here we have two equations. Equation 12.26 is just a repeat of the Pearson correlation coefficient. It is the ratio, and in the numerator, we have the sum of x sub I minus x bar times the quantity y sub I minus y bar. And in the denominator, we have the square root of the product of two terms. The first term is the sum over the quantity xi minus x bar squared times the sum over the quantity xi x sub I minus x bar squared. So that was equation 12.26. Again, that's just the formula for the Pearson correlation coefficient. Then we have equation 12.27 that reads S sub c equals cosine of theta equals a ratio where the numerator is the sum of x sub I times y sub I, and the denominator we have the square root of the sum of x sub I squared times the square root of the sum of y sub I squared. Back to the text. I'm sure you figured out that the two formulas are identical when the data are mean-centered. When there are mean offsets, the two measures will differ for reasons I will explain below and you will discover empirically in exercise 9. The impact of this is that cosine similarity and Pearson correlation coefficient can be identical or very different. Consider the following example. Here we have a series of equations. First, we have x equals the data set 1, 2, 3, 4. Y equals the data set 1, 2, 3, 4. And z equals the data set 101, 102, 103, 104. Then we have r sub xy equals r sub xz equals s sub c of x and y equals 1. In other words, the correlation between x and y is 1, the correlation between x and z is 1, and the cosine similarity between x and y is 1. But then we have the next equation which states that s sub c of x and z, remember x was 1, 2, 3, 4, z was 101, 102, and so on, that cosine similarity is 0.91. Back to the text. The correlations are identical because the variables x, y, and z are identical when mean-centered. However, the cosine similarity does not mean-center, and so the numerical relationship decreases when there are mean differences. Interpretation. You might remember from trigonometry that the cosine of an angle between two vectors is bound between -1 and +1, equals -1 when the two lines meet at 180 degrees, equals 0 when the angle between the two vectors is 90 degrees, this is also called orthogonal, and equals 1 when the two vectors are parallel. If you imagine that a variable is represented as a vector, then the angle between the two vectors in an m-dimensional space encodes their similarity. Where does cosine similarity come from? If you have a linear algebra background, you might recognize cosine similarity if presented using vector notation. Here we have equation 12.33, which states that the cosine of theta equals x transpose y divided by the norm of x times the norm of y. This is the geometric definition of the dot product, rearranged to solve for the cosine of the angle between the two vectors. Cosine similarity versus Pearson correlation. How should we interpret the difference between Pearson correlation and cosine similarity, and is one quote-unquote right and the other quote-unquote wrong? Well, of course, they're both correct. They just indicate slightly different things about the relationship between two variables. From the perspective of the Pearson correlation coefficient, we care about whether the data values go up and down together, regardless of their scale or units. The perspective from cosine similarity is that if two variables are numerically different from each other, then they are less similar to each other, even if they go up and down together. When should you use correlation versus cosine similarity? Let's take height and weight as an example. The correlation between height and weight is identical regardless of how you measure height, so inches or feet or centimeters or light years, and regardless of how you measure weight, so pounds, stones, kilograms, and so on. However, the cosine similarity between height and weight will depend on the measurement units. Therefore, you should use correlation when you're interested in a relationship between two variables that are in different scales, and you should use cosine similarity when you are interested in the numerical correspondence between two variables that are in the same scale. That said, cosine similarity is not often used in statistics, and I won't actually discuss it again in this book except for exercises 8 and 9. I included it here because it is an analysis worth knowing, and because understanding the difference between cosine similarity and correlation helps you understand correlation. Section 12.11, Exercises. As you now know, I describe the exercises and their solutions in videos that are in my YouTube channel. I encourage you to go check out those videos. End of chapter 12.